Hi, my name is Annalisa Szymanski. Today, I'll be presenting our paper titled Integrating Expertise in Large Language Models, Crafting a Customized Nutrition Assistant with Refined Template Instructions. This work is supported by the Food Information Networks project at the University of Notre Dame and in collaboration with the Nutrition Science Department at Purdue University. There is a wealth of food information available to consumers when making food choices. Consumers must interpret nutrition facts labels, food product ingredients, health claims, government guidelines, and align this information to their specific health needs and cost constraints. This is even more difficult in communities suffering from food insecurity, language or literacy challenges, and high incidence rates of chronic diet-related diseases. Personalized dietary advice from dietitians has been shown to enhance nutrition education and informed decision-making. However, such professional advice is often unaffordable, which widens the gap in nutritional knowledge and access to healthful dietary choices. Large language models could offer a potential solution. For example, we could prompt a large language model, such as ChatGPT, to give a detailed description of the nutritional and health qualities of a food product that are tailored to an individual's dietary and health needs. We refer to this as a food product explanation. This could be particularly helpful in regions where the translation of nutrition information may be scarce or unavailable. Existing literature has shown that large language models have been used for meal planning and recipe generation. However, some studies have shown that these models exhibit bias, misunderstandings, or non-evidence-based information. In addition, there have been limited work with conducting rigorous validations and involving experts in the process to validate food-related outputs. Our main objective is to engineer LLMs with dietitians. In this paper, our first objective is to understand and evaluate the capabilities and limitations of LLMs in generating food product explanations, and we do this by focusing on the dietitian's perspectives and evaluations. Second, we formulate design guidelines based on dietitian feedback that can then be used to better prompt instruction for providing food product explanations. And third, we implement our guidelines in a customized GPT prototype and refine the instructions in a collaborative focus group with dietitians. In the first phase of our study, we looked at the following research questions. First, what are the advantages and limitations associated with the use of LLMs for producing explanations for various food products? Second, in the context of utilizing LLMs, how does the specificity of information given in the input prompt influence the effectiveness of the generated explanations? And third, what design guidelines should be prioritized when applying LLMs for translation of dietary information for consumers? To answer these questions, we first generated food product explanations through GPT-4 for 5 different food products. These prompts were crafted with a nutrition scientist on our team. Then, we recruited 12 registered dietitians for a 90-minute interview. Through this, dietitians were asked to evaluate 5 product outputs across 3 levels of specificity. Our goal was to test the adaptability and precision in generating tailored explanations with more or less information given in the prompt. At each level, the model was asked to focus on 5 factors that we kept the same for each food product. Then, the lowest level of specificity, level 1, included only the product name and size. Level 2 included the addition of the nutrition facts label and ingredient details. And lastly, level 3 included the addition of a hypothetical user's dietary needs. We collected Likert scale surveys for each of the product outputs across 3 levels of specificity. We report the means and standard deviations, which can be found in our paper. We also coded the interview data on dietitian evaluations into themes and key findings with members of our research group. In this presentation, we will focus only on the qualitative findings. For quantitative measurements, please refer to the paper. Now let's move on to some of our key findings. Our first key finding was that the outputs generated by more detailed specificity prompts are preferred by dietitians. This is because Level 2 and Level 3 specificity outputs reference the actual nutrition information and personalize the information to the user. The Level 1 outputs were overgeneralized and lacked reference to specific nutrients. For instance, the output was unable to specify that a product was gluten-free without the presence of the product labels. To mitigate this problem, we suggest that all prompts must be provided with product-level information to provide a more accurate output, and this includes the nutrition facts label and the ingredient list in the prompt instructions. Key finding 2 indicated that the outputs do not align with the standards upheld by registered dietitians. During the interviews, dietitians found concerns about the overall reliability of the output in producing accurate information, as well as the sources of information that it was pulling from. For example, allergens were discussed indiscriminately, using terms such as may or can include a specific ingredient, which lacks certainty. In addition, the outputs did not appear to pull from sources that dietitians considered appropriate, which could be the cause of these reliability concerns. To fix this, we implemented example template sentences to structure the output. This involved including example sentences that explain the presence of a specific ingredient in relation to the specific allergen-free diet. And these example sentences were instructed to be included only when an allergen was present, to be more definitive and to explain appropriately to the user. This also indicates the design guideline that the prompts need to include foundational evidence-based sources, such as the Dietary Guidelines for Americans, as well as the Transactional Education of MyPlate, which provides food group guidance. Both of these sources are provided by the U.S. Department of Food and Agriculture. The Dietary Guidelines for Americans also incorporates information on nutrients based on the dietary reference intakes for nutrient information. This is used to remove concerns about inaccurate referencing of nutrient levels and how they relate to specific diets. Next, key finding 3 showed a prevalence of falsehoods that undermine the clarity and coherence of the explanations and could lead consumers to form incorrect conclusions. This includes imprecise buzzwords, prevalent errors, misleading statements, and fictitious substitutions. For example, one output stated that a product was unsuitable for a low-sodium diet when the product did fit the low-sodium federal guidelines. There were also indications that the products that were lactose-free or organic products were healthier, and this raised a concern among dietitians. Due to this, we designed prompt instructions to limit buzzwords such as healthy dose or muscle growth. In addition, we propose to specify guidelines on nutrient content. This includes providing example template sentences to categorize low or high amounts of a nutrient. And in this case, we are providing the GPT with ranges as a reference for labeling a nutrient such as sodium as high or low. Key finding 4 states that the model fails to maximize its comprehensiveness and educational value of its output. There were concerns about using the term daily value percentage when describing the nutrients because it's based on a 2,000 calorie diet, which is not appropriate for all users. In addition, there were also concerns about the overall reading level of the outputs and how that could be interpreted by the users. We propose incorporating instructions to represent a holistic view of each food product in relation to daily dietary goals. This includes first stating whether or not the product is suitable for a user's diet before any explanation. In addition, we instruct the LLM to discuss how the product fits in relation to the MyPlate food groupings. Second, the GPT should be provided with functionality and scope. For example, we recommend instructing the GPT to emulate a virtual dietitian. This includes instructing it to act more as an educational tool that explains the healthiness of the product in relation to a specific dietary need. In addition, due to the reading proficiency of users, we suggest the GPT use a 5th grade reading level when educating the users so that it's understood by all reading levels. Lastly, Key finding 5 shows that the outputs undermine potential alignment with consumers' immediate needs. Yet it does not provide information on broader contextual factors or integrate insights into an individual's comprehensive diet. For instance, the outputs did not address how the food product could be paired with other foods to increase nutritional value, or how commonly paired products could introduce new allergens and make the product unsuitable. For example, cereals are generally paired with milk, which should be considered by a lactose intolerant individual. We propose to instruct the GPT to include comprehensive nutritional guidance and food pairing suggestions. This includes providing template sentences that emphasize the importance of food pairings and balanced daily nutrition. In phase 2 of our study, following our design guidelines, we created and implemented an initial set of template instructions and knowledge sources into a customized GPT prototype. The GPT allows the designer to modify instructions, which include the example sentences that were mentioned before. And in addition, we can attach files to store information for the model to pull from, such as the dietary guidelines and nutrition label information. This prototype allows us to input a product along with dietary guidelines to then produce food product explanations. We conducted 2 focus group sessions. The dietitians evaluated the output produced by the template instructions, and then where necessary, they made changes to the template instructions in the GPT prototype platform. They then saved the changes and then re-evaluated the new output. This was done in an iterative cycle until the output reached full approval. In the focus groups, the dietitians made several refinements that improved the food product explanations. First, they wanted the outputs to follow a consistent format, structure, and organization that would mimic how they would provide information to a client. And this included incorporating an immediate product rating, organizing the information into specific headings, and also following a bullet point structure. Second, the dietitians suggested the addition of further example template sentences to bring more simplified nutrient information. For instance, the output now provides specific nutrient information listed in milligrams or grams as opposed to the daily value percentage, as guided by the RDs and how they relate to a user's set of dietary goals. Third, a large amount of errors originally observed by dietitians were mitigated with the incorporation of example sentences into the prompt. And last, additional knowledge sources were provided to be referenced. This included referencing nutrient claim documentation for ratings of products as low sodium or fat-free. Our research shows the importance of expert validation and collaboration in the design and implementation of LLMs such as GPT-4. Initially, our validation study showed several concerns with the outputs. However, the dietitians were crucial in identifying these errors and giving us the information needed to design guidelines for prompt instruction aimed at mitigating these issues. In addition, the real-time iterative development in Study 2 proved to be effective in the overall accuracy of the output. It allowed the dietitians to see firsthand how changes to the template instructions affected the output. The focus groups brought a dynamic component to the development of the prototype by incorporating expert insights. The end result is a customized GPT prototype developed in collaboration with dietitians. We call this prototype the Food Product Nutrition Assistant. Our study shows detailed template instructions that consider dietitian standards prove to be effective. While we may not be able to say that it is completely error or bias-free, we have shown a way to handle common errors and make outputs more accurate and consistent. In addition, the knowledge sources recommended by dietitians are now effectively referenced in the output, and this shows that even more can be done with knowledge sources of customized GPTs in various fields. We highlight the importance of collaboration with experts in developing LLMs for food product explanations. Our study shows that by understanding the nuances of GPT outputs from expert lenses, that we can craft customized GPTs using template instructions that enhance the generation of food product descriptions and personalized nutrition information. Thank you.